questions yet for the mocks up there? I'm preparing some video solutions to them. So those will be going up quite soon to the 2 mock papers up there. But we have a few things to say to finish off this chapter 4 on the derivative and associated matters. There's 2 application areas we want to look at later this morning, which is in the area of curve sketching and some kinematics type problems. Well, first of all, I want to make a few remarks, which is based off the alternative definition of the derivative we gave, that linear approximation and error viewpoint of the derivative, which is quite useful. And the first of these concerns Taylor series. So we briefly mentioned Taylor series when we were studying series in the first term. Taylor series are an example of what are called power series. So power series is the term used for when you've got a series defining a function. So series is a sum of terms, or we're mostly dealing with our sums of infinite amount of terms. So if your series involves a variable such as it does here, x, so some unspecified variable x, and that's defining a function, then that is termed in general a power series. Now we're particularly interested in, or the main example of power series that arise for functions of a real variable in this kind of calculus setting, is the so-called Taylor series. So these are power series representations for functions. And so they're infinite polynomial representations for functions, and the coefficients of them are the various derivatives of the functions. Okay. So Taylor's theorem, or the Taylor series theory, says that if you've got a nice function f, nice continuous differentiable function f, we can express probably at least in some interval around a base point a, we can express nearby values of the function f of a plus x. We can express those in this power series form. Okay. We've got this infinite series of powers of the x variable. It's an infinite polynomial in x, and the coefficients are these f superscript bracket n evaluated at a. So f superscript bracket n refers to the nth derivative of x evaluated at the base point a. These are scaled. These are divided by n factorial. Okay, where n is the summation of x going from 0 through to infinity. Now, as a special case of these, the term Maclaurin series is often used for the special case of these where the base point a is the origin of 0. Okay. So that's like that's a simplified or a particular instance of the Taylor series that is often talked about. Okay. So here we would be expressing the value of the function f at a point x, maybe close to 0, expressing it as an infinite polynomial of x. Now, this issue of whether it's close at any point x or at some point x close to the base point, it depends on what the function you're dealing with is. Okay? So here we're presented with various Taylor series, or various Maclaurin series, really. Although this logarithm, I think it was the Taylor series. Various Taylor series anyway, for various standard functions, but each of them have a condition on the value of x. Okay, each of them have a domain of validity for x. Okay, so for instance, this one for 1 plus x to the r, these kind of binomial type expansion, is only valid for values of x between -1 and 1. The exponential sine and cosine Taylor series are valid everywhere, for all values of x. Okay. And this logarithm one, which expands the logarithm function around the base point 1, this is only valid for variations x between -1 and 1. Okay. And the Taylor series for tangent function is only valid between -π/2 and π/2. So these are sometimes called radius of convergence. So the radius of convergence is the distance from the origin in which the Taylor series is valid. Now, all I'd like to show you in addition to that is, now we're not going to do a full proof of Taylor series, full proof of their existence and justification of them involves a lot of technical details. But what we will say is we'll compare this, or we'll compare these to our linear approximation plus error view of the derivative. Okay, so you recall we expressed the value of the function x, sorry, the value of the function f at a point a plus x close to a base point a. When we did our alternative view of the derivative, we found that the derivative was this unique number which multiplied x and was the kind of order 1 term in this linear approximation to this new value of the function f. So the value of the function f at a point close to a is the value the function has at a, is the kind of 0th order approximation, plus this variation term, which is a multiple of x. Okay, it's order 1 term x. Okay, and the coefficient of x here in this approximation is the derivative of the function f evaluated at the base point. Now, this equation isn't true yet. Sorry, I shouldn't put a full stop there. This equation isn't true. It's an approximation, so there's a certain error associated to it, and the error term, total error term, has this form x times epsilon of x. Okay, so this is the linear approximation, and this here is the error term. The error term has this nice property that not only does the error term converge to 0 as x goes to 0, because we would expect the error term to converge to 0. Because as x goes to 0, we're talking about estimating the value of f at a point close to a. If you're making the point close to a get closer and closer to a as x goes to 0, then since you're approximating it with f plus f of a and something depending on x, as x gets smaller and smaller, you'd expect the error in this approximation to go to 0. And it does go to 0, but we get even more than that. Not only does the error term go to 0, but the error term divided by x, which is this function epsilon of x, this also goes to 0 as x goes to 0. So the error term is this kind of second order convergence to 0 in x. Okay. So that's a reminder of this linear approximation plus error view of the derivative. And this does agree, or this does fit with Taylor series. Okay, because if you apply the Taylor series formula to f of a plus x, you apply the Taylor series formula to f of a plus x, taking it from the notes there, it's this infinite polynomial in the variable x, and the coefficients are the nth derivative of f evaluated at a divided by n factorial. Now, if you expand that, if you write out that sum, write out the first few terms. The first term will be the 0th derivative of f evaluated at a over 0 factorial. The next term will be the first derivative of f at a over 1 factorial by x. Then you have second derivative at a 2 factorial x squared plus, let's finish with this one, third derivative of f at a over 3 factorial x cubed, and so on. Now, but what are we seeing here? Well, what is the 0th derivative of f? F differentiated 0 times is just f itself. 0 factorial is defined to be 1. It's an empty product, so it should take the value 1. Just as empty sums take the value 0, empty products should take the value 1. So by convention, 0 factorial is defined to be 1. So this first term is simply f of a. The second term, well, 1 factorial is 1, and then we've got the first derivative of f evaluated at a times x. So we again see exactly our linear approximation. So far, the Taylor series is tallying with our linear approximation and error view. So that means this stuff, so if these first two terms are the linear approximation to the new value of f, that means all this other stuff probably, or it should fit in, it should be that error term up there. So to make it fit that picture, we should be able to divide that by x and still see it converge to 0, even after we've divided it by x. And it is easy to write down anyway to take a factor of x out of this, because you've got x squared, x cubed, x4, and so on. So we can, on paper anyway, factor out a factor of x out of that. And what's left behind is the second derivative of f at a over 2 factorial times x. The third derivative of f at a over 3 factorial times x squared, plus etc., etc. So this is our error term here, all of this. And this bracket will be the function epsilon of x. And what's the behavior of epsilon x as x approaches 0? Well, each term is approaching 0. So, I mean, it is an infinite series, so you'd have to worry about what it's doing as an infinite series, but you could apply build an argument based on the ratio test, I think, to prove the convergence of that. But just using a hand-wavy argument or a vaguish argument, we see it as a polynomial with beginning at x. You got x squared, x cubed, x4, and so on. So as x approaches 0, all those terms are going to be approaching 0. So, okay, well that's not a rigorous proof of convergence, but it does maybe suggest. We can show that epsilon of x also converges to 0 as x goes to 0. But it at least demonstrates that the Taylor series view, our series for values of the function f in a nearby point, it fits nicely with what we had already fairly rigorously derived as our alternative version of the definition of the derivative, which was the derivative was the unique number that went in there that provided a linear approximation such that the error term had this kind of extra convergence to 0 part. The error term still converged to 0, even after you divided it by x, that epsilon x converged to 0. So we see a similar thing happening in the, see the same behavior from the Taylor series representation as well. And while we're on it, before we go on to the other application areas, I just wanted to say a little bit about L'Hopital's rule. So the linear approximation plus error view also provides a justification of L'Hopital's rule. Okay. Remember, L'Hopital's rule was when we had both how do I say this? Yeah, when we had both f of a plus x and g of a plus x, both converging to 0 as x converge to 0. i.e., two functions with f of a equal to g of a equal to 0. When you got two functions that are 0, sorry, yes.
Yeah, I was just going back to the approximations.
Yeah.
I was just saying, does that then mean that the higher the order of the approximation, the smaller the error term? Yes. So if we wanted to approximate, the error term is going to get smaller.
If you took in more and more of those terms of the Taylor series and packaged them up is your approximation. Okay, it would no longer be linear. It would then be an order 2 or order 3 or 4. The error term will get less and less. Yeah. So that's true as well. So with Taylor series, so it's an infinite polynomial, but if you cut it off at some point and say, well, I'm going to take these 4 terms up to x cubed as my approximation value of the function f, then it will be a better approximation than just taking the first 3. Because it's kind of taking account of more information. It's taking account of more information about the behavior of the function. And the more and more information you take in, you'd expect your view to get better and better. And that's true in this case. So there are, when you look at the precise statement of Taylor's theorem, not only does it state this, that the infinite polynomial is equal to the function, it also gives a precise statement it gives you more information or more ways to think about the error term when you cut the polynomial off at some finite. So that's something to look into as well. It's something we might look at in next year in detail as well. But yeah, that's true. The more and more terms you admit into your approximation, although it will no longer be linear then, but the better and better the approximation gets. Yeah, that's true. That's a good point to make. But then, for lots of applications and lots of mathematical modeling, we do like linear approximations because they're so easy to deal with. And all of the theory of linear algebra, matrices and matrix decompositions and eigenvalues and whatnot, they are all applicable to linear approximation cases, especially when you go into higher multivariable functions. The linear approximations, although in some ways you think of them, well, why are you stopping at order 1 approximation? You've got all this other information you might take account of. But we've got such a good kind of theoretical basis for dealing with linear stuff. That's the whole subject of linear algebra and vector spaces and matrix manipulation, that you can do a lot of good work and you can successfully derive a lot of things when dealing with linear approximations, which is much harder to do with higher order approximations. Even though from an evaluation viewpoint, they do give more accurate answers, but then it's harder to argue. But that's a viewpoint that you'll see developed in 2nd and 3rd year in the numerical analysis courses. Okay, so coming back to L'Hopital's rule, we had this problem about what to do with the limit as x approached 0 of these expressions here, of say f of a plus x over g of a plus x. Normally, we can apply our algebra of limits theorem, the quotients part, to say the limit of a quotient is the quotient of the limits. But what happens in the case where the 2 functions you're using to build the quotient, they both take the value 0 at the limit point? Okay, as x approaches 0, f of a plus x is convergent to f of a, g of a plus x is convergent to g of a. But we can't say the limit of the quotient is 0 over 0 because that's nonsense. It doesn't make any sense. What is 0 over 0? It doesn't have a definition. But if we bring in this linear approximation plus error viewpoint, f of a plus x, we have this alternative view of it. It's going to be f of a plus the first derivative of f evaluated at a times x plus our nice error term. X times epsilon x, where epsilon x goes to 0. And you've got a similar thing. You'll have a similar thing for g. If g is differential. The g of a plus x would be g of a plus the derivative of g at a times x plus x, and it will have its own error function. I'll use a different symbol for it because it's a different function. Okay. So for epsilon x and lambda of x both go to 0 as x goes to 0. X goes to 0. So we look at this representation of the original limit that we're trying to do. And now it's easy to make use of the fact that f of a and g of a are 0. Because we can just forget them from these expressions. If they're 0, we don't have to include them. And then, so then you're looking at the limit of this quotient, and there's an obvious simplification we can do to that quotient. You see both the numerator and the denominator clearly have a factor of x in them. That's easy to take out, okay? Because it's a sum of 2 terms, both of which are multiples of x, and that's the same down here. We're taking a limiting process as x approaches 0. So x is never actually equal to 0 in this limiting process. So we're free to divide by x. No problem with that. So once we take account of the fact that f of a and g of a are 0, this is now the quotient. So we can divide above and below by x. And we have f prime of a plus epsilon x and g prime of a plus lambda x. And that we can apply, well, assuming these two derivatives are non-zero, to that we can apply the algebra of limits theorem, okay? Because the limit of epsilon is converging to 0 and lambda is converging to 0. So this will be equal to the f prime a over g prime. Because these terms no longer depend on x now. The derivative of f at a, the derivative of g at a, they no longer depend on x. So we can say it's equal to that since epsilon and lambda go to 0, and provided g prime a is not 0, and f prime a is not 0. Then it'll be equal to that. I mean, if the g prime a was not 0, but the f prime a was, well, then the whole thing would be converging to 0. So it probably would be, so yeah, it would still be a valid expression. Yeah, I don't have to insist that that's not 0. If the derivative of f was 0, we'd have 0 over something non-zero, so we'd have a 0 limit, and that would be the correct conclusion. But if the g prime of a was still 0, you may, and the f prime a wasn't, then you'd have something finite over something 0. The conclusion then would be that that limit is going to infinity, so to speak. It's an unbounded limit. It's something finite divided by something that's converging to 0. So in that case, the conclusion would be the limit is infinity, either plus infinity or minus infinity, depending on what the sign of the f prime a was. And then that would be the correct conclusion to the original limit. But in the case where they were both 0, that wouldn't make any sense, but it kind of, it replicates the problem, and we'd be able to apply L'Hopital's rule again. So we get a justification. Get a justification for the L'Hopital's rule. The other cases in which it applies, if both the functions converge to infinity at the base point, they can be dealt with using some other more detailed techniques. But at least that's another good thing we can extract out of this linear approximation plus error view of the derivative. Okay. So what I'd like to do now is return to the final two applications of the derivative that we're going to consider in the notes. So this begins on page 65. This is the subject of curve sketching. Now, the topic of curve sketching is kind of been overtaken somewhat with the advent of nice mathematical software packages. Okay, you can put in more or less any function into a mathematical software package such as MATLAB or Sage or number of equivalents. Even if you type into the Google search box, even on your phone's plot, if you typed into the Google search box plot this expression 3x squared minus 7 / brackets 2x plus 1, it would on your phone fairly quickly give you a nice, reasonable, zoomable, pannable plot of the function. Quite a useful thing if you've just got your phone with you and you're analyzing functions. Right? Whereas, in the pre-computer days, people were concerned a lot with being able to plot, graphs, plot sketches of these graphs that accurately portrayed some of the qualitative features, at least, of the function. But it's still a useful thing to think about and to have in mind and to appreciate what the relevance of the derivative for it would be. So the kind of, you can do it at various levels, but these bullet points here would list some of the main aspects of or the behavior of a function that you might want to obtain before attempting to sketch what the curve might look like. So for instance, first of all, you'd be concerned with the validity of the function, what the domain of the formula should be. So with this f of x, you see there is a problem with one of the points x equals minus a half. But x equals minus a half, the function is undefined. You should be aware of that. Okay, so it's probably got some interesting behavior close to x equals minus a half. Because when you're very close to x equals minus a half, the numerator will be close to something, 3/4 minus 7. But the denominator will be very, very close to 0. So the function f will be exploding in value as you get closer and closer to x equals minus a half. So that's very relevant information to have about that. So that's the second bullet point. How is f behaving close to these undefined points? Is it exploding in value? Is it getting closer? Is it exploding in the positive direction or in the negative direction? And on which side of that undefined? Then we might want to know what our function looks like relative to the coordinate axis. So we might want to evaluate, if we can, f of 0, because that would be the point where it crosses the y-axis. And we might want to solve, if we can, f of x equals 0, because that would be where the function is crossing the horizontal. We also want to know about any other asymptotes of the function. Okay, the long-term asymptotes of the function. As the argument to f gets larger and larger in the positive or negative direction, is there some limiting curves that the function is approaching? Because if there are, they might help you inform your sketch and indicating some of the long-term behavior. Then here is where the derivative starts to come in, to talk about stationary points. So any turning points, any local or global minimums or maximums of the function, that would be good information to accurately depict on the sketch as well. And then at least making sure your sketch accurately represents the correct sign that the function is taking on the various parts of the domain. If you've got various undefined points, you'll have various sections of your domain, and at least know what the sign of the function is in those points, whether the function is large or small on those points. Any of the asymptotic lines, is the function approaching those from below or from above? That would be more accurate information to obtain as well. Okay, so there's a worked example here for this function that we've been looking at that gets all this information. So one of the so we've got this undefined point at x equals minus a half, so that should be excluded from the domain. And so then what's the function doing close to that? Okay. Well, when x is less than when x is close to minus a half and less than minus a half, to the left of minus a half, then the denominator is going to be small but negative. So when x is less than minus a half, it's bigger in absolute value than minus a half, but it's negative to the left of it. Then the denominator, okay, it's going to be small. It's going to be nearly minus 1 plus 1. But the 2x part will be slightly bigger than minus 1. It'll be slightly to the left of minus 1. So the denominator will be small and negative. Now, the f of x, when x is close to minus a half, as we've said, f of x is going to be close to 3/4 minus 7, which is a negative quantity. So when x is to the left of minus a half, you're going to have negative over negative. Okay? But a finite negative quantity divided by something very small and negative. So you're going to be exploding in value towards plus infinity. But on the other hand, if x is to the right of minus a half, then the denominator will be small but positive. Okay, and it's still got a negative numerator, so that means the overall value will be negative, but exploding because it's going to be something fixed and finite divided by something very small, so it's going to be exploding towards negative. We can find the axis crossing points. We can evaluate f of 0. That's simply minus 7. You see there, so it crosses the y-axis at minus 7. We can solve for when the function is 0. Now it's a fraction, so it's going to be 0 when the numerator is 0. That's very easy to solve. 3x squared minus 7 has got roots at plus or minus square root of 7/3, which is whatever it is, plus or minus 1.5 approximately. And then we come to the issue of asymptotes. That's something, so we need to divide, if we can, the numerator by the denominator. Okay? And that's something sometimes people struggle with. So I might just show the derivation of that on the page. But we can re-express f there. Now, why am I expressing it like that? Because that gives an expression for f as, well, 3 over 2x minus 3/4. That's a line, isn't it? Y equals mx plus c. So these first two terms is the equation of a line. So we're expressing f as a certain line plus an adjustment. But the point about the adjustment is it's some number over 2x plus 1. So the adjustment, or the error, if you like, converges to 0 as x gets larger and larger. As x gets larger and larger, this quantity here will be converging to 0. So the values f of x will be getting closer and closer to the values of that line. So that's an asymptotic line for the long-term behavior of the function f, both in the negative direction and the positive direction. I just want to quickly demonstrate how we arrive at those 3 over 2 and 3/4. Sometimes people need a little bit of help with that. So this is example 4.11. So in example 4.11, so 3x squared minus 7 over 2x plus 1. So we'd like another expression for this. Okay. Now there's various ways people might have seen this, the various ways of sending it out, but we basically want to do some kind of long division, dividing 3x squared minus 7 by 2x plus 1. But you may have learned a way to set this out, but there's another kind of way you can approach it, or that way will be equivalent to this. So we're going to attempt to write 3x squared minus 7 as a multiple of 2x plus 1. We want to write it as some kind of multiple of 2x plus 1 so that we can divide it by 2x plus 1. And we may have to build this up in stages. First thing to think about getting right is this 3x squared term. What would you have to multiply 2x plus 1 by in order to generate that 3x squared? Well, you'd have to multiply it by 3 over 2x, wouldn't you? You multiply it by 3 over 2x, 2's will cancel, and you'll get 3x squared. You'll get your 3x squared. Okay. Now, the equation isn't true yet. The right-hand side does indeed generate 3x squared, but it also generates 3 over 2x when you multiply that by the 1. And the 3 over 2x is not there, so we'd have to immediately subtract it again. And also what the right-hand side misses is it misses the minus 7. So we'd have to subtract 7. Now the equation's true. So we've kind of written part of 3x squared minus 7 as a multiple of 2x plus 1. We can still do some more work because this is an order 1 bit in x here, and this is order 1 in x. So we should be able to achieve this with some kind of multiple. So we can, let's just leave this like that for the moment. But we'll attempt to write the rest of it now, again, as some multiple of 2x plus 1. Well, how do you get minus 3 over 2x out of 2x? Well, you've got to multiply it by minus 3 over 2. No, minus 3 over 4. Okay, if you multiply this bracket by minus 3/4, 2 cancels, you get minus 3 over 2x. Good. That gives you this part. Of course, it also gives you minus 3/4. But what we really want is minus 7. Minus 7 is what? 28/4. Minus 28/4. We've only generated minus 3/4. So we need an extra minus 25/4. So that's good. I mean, Okay, we've complicated our representation of 3x squared minus 7, but we've complicated it in an appropriate way in order to divide it by 2x plus 1. So we've got it as 3 over 2x minus 3/4, all multiplied by 2x plus 1. And then we have this final remainder term, which is a constant, 25/4. Now, we won't try dividing that by 2x plus 1 because if you want to generate polynomial parts, you know, if you multiply 2x plus 1, you're going to generate x parts. And this, all we have is a constant. So we've got the kind of smallest remainder possible. In general, what you're looking to get here is a remainder polynomial which has smaller degree than the one you divided by. So we've divided by this polynomial 2x plus 1, which is order 1, and we've got a constant which is order 0. If we were dividing by a more complicated polynomial, a cubic or a quadratic, order 2, you'd be looking to get your remainder as having degree strictly less than the degree of what you're dividing. Because now we can say, now we can express f as x is, so my denominator is still 2x plus 1, but now I have this expression in the numerator. 3 over 2x minus 3/4 times 2x plus 1 minus 25/4. Now that's a fraction with I regard this as just being one chunk in the denominator, but I've got 2 bits in the numerator, so I can separate the fraction, actually, just using the rules for addition of fractions. Minus this 25/4, 2x plus 1. And of course, now these two factors, the 2x plus 1, disappear. So you simply got minus 3 over 2x minus 3/4 minus 25/4 over 2x plus 1. So this is an asymptotic curve, or in this case specifically, it's a line, but more general, it might be a general polynomial here. But it's an asymptotic curve for the function f, because we've expressed f as this curve plus an error term, and the error term converges to 0 as x goes to plus or minus infinity. So the long-term behavior of x gets big in magnitude in either direction. So that long-term behavior, we can really, this error term becomes less and less significant. It's converging to 0. So it becomes more and more the case that f of x is approximately this long. So that line is going to be an asymptotic curve for it. More complicated cases, you could get a higher degree polynomial in your asymptotic curve. But you're always looking to find some kind of curve plus an error term that goes to 0. Okay, so this kind of process up here was just some kind of step-by-step process that attempts to write the numerator as much as you can in terms of the denominator. In terms of meaning as some multiple of the denominator, so that you can effect the division and get some kind of more easier to handle curve here and some associated error. Some of you may have learned how to actually do this as an imitation of long division with numbers, and you can set it out like that. You learned long division of numbers like this. You can do exactly the same thing with polynomials. You attempt to divide this by this, divide it by a certain amount, you multiply it through, subtract, you get a remainder, then you attempt to do the division again. And it basically just imitates this process that we went through with the equations at the top. You select the multiple up here, and eventually get some final remainder which you won't be able to divide by 2x plus 1 at all, which would be the minus 25/4. Okay. So to complete looking at that curve sketching example, we then go on to find the stationary. So that's our asymptotic curve representation. And we can also think about what sign the error term has. As x gets greater and greater in the positive direction, this error bit, well, it's got a minus sign in front of it, so it's going to be small and negative. Right? As x gets closer, gets further and further towards plus infinity. As x gets further and further towards minus infinity, the total error term there is going to be positive. Fraction bit is going to be negative because there's something over 2 times something large and negative plus 1. So the fraction will be negative, but then the negative sign in front of it turns it to be positive. So with that information, you know where the graph of the function is relative to the asymptotic line, whether it's above, converging to the asymptotic line from above, okay, with a positive error term, or converging to the asymptotic line from below, where there's a negative error term. Finally, we bring in the derivatives, and we get the stationary points of this function. So, skipping over the details, it's indicated the usual method. We look at the derivative of f. There's this expression here. We solve the derivative equal to 0. So we just take the numerator polynomial and solve it equal to 0. Turns out, in this example, the discriminant of this quadratic is negative, so there are no turning points in this particular example. So putting all the, okay, so it kind of ends, unfortunately. Unfortunately, I show a computer plot of the curve at the end. But at least in this computer plot, we can pick out the various aspects that we discovered there. So we can start to see here the presence of the asymptotic line. The asymptotic line, see, as you get larger and larger, the curve is straightening out. And in the negative direction, the curve seems to be straightening out. If you zoomed out of that, it would become more apparent. If you plot this on computer and zoom out a lot, you see the main kind of obvious feature is just this single line, which is slope 3/2. So that single line that will be becoming apparent there as you zoom out and out will be this line here, 3/2x minus 3/4. So our error terms is going to 0. And we can see other aspects, the approximate value where it puts the x-axis, those 2 points, which was plus or minus square root of 7/3 and so on. And it's crossing the y-axis. It was crossing the y-axis at -7, wasn't it? Yeah, -7. So it certainly seems to be heading towards that -6 down here, not yet across the y-axis. Okay, so there's some more examples for you to try here in these exercises 4.2 and towards the back of the notes as well. So what we'll do is next week, you'll have me for 2 lectures next week. In the first lecture, we'll deal with the kinematics applications. And then I'll use my second lecture next week for doing some revision activities for the test. And you will have the video solutions to the 2 mock papers by then. Okay, so thanks for your attention, everybody. And I shall see you next week.